So hello everyone and welcome to week number 10. This is now lecture number 19. I'm going to share my screen and we are on chapter 14 on what's called the normal model. The normal distribution or the normal model is without question the most important distribution in statistics. It occurs all over the place, both as a distribution in its own right and as an approximate distribution for many other situations. Okay, this one is extremely important. And I don't know who necessarily discovered it, but the normal model is also called a Gaussian after Carl Friedrich Gauss, the greatest mathematician of all time. So either he discovered it or at least he publicized it or used it to such an extent more than anyone else that he had his name attached to it. A normal distribution is also called a bell curve. And I'm hoping that sometime in your life you've heard the term bell curve before. A bell curve is essentially a normal distribution that has the properties that its value at some location is, or the probability of having a value at some location is high, and it quickly tapers off to both sides. Not necessarily quickly, it depends on the situation, but it can taper off on both sides from the peak. So if we look at the picture that we have here, what we have is verbal plus math SAT scores from a 2013 group of seniors who took the SAT. It doesn't quite say how many, but it could be all of them because we're looking at a huge number here. Hundreds upon hundreds of thousands of students. So this might be a grouping of all of them. And what we can see is at least approximately a very bell curvy shape, this normal distribution shape, which peaks at what location, roughly?
1,000?
Roughly 1,000. And if you actually look right above the picture, it's a little more exact. It says 1,011. But you can't get that from looking because it's hard to eyeball these types of things, with a standard deviation of 216. And we are going to see how to compute both mathematically and well, not mathematically, but we're going to see how to get a graphical approximation for the standard deviation. One thing I do notice when I look at this is it's not perfectly bell curve. It kind of looks like on the right side to have a little more of a tail than on the left. Do you see that, or is that my imagination?
No, I agree.
Yeah, the tail seems a little skewed, but it's approximately normal at least. Okay, and quite often in math classes, you'll hear the term it's normal or it's approximately normal, and in which case you just assume it's normal and you don't worry about real life scenarios that where it might not be. But a bell curvy shape is a normal distribution. Okay, so when we talk about the normal distribution, you're going to have three numbers that are commonly paraded around, and those numbers, which I'm sure are here somewhere, but I'm going to give them to you right now either way. Those numbers are the following three numbers. And these three numbers appear so often. They are 68, 95, and 99.7. Okay, these are the three numbers that deal with the normal distribution in a way that I will explain in just a second. Once I figure out how to move this thing. Okay. So the mean is right in the center. Okay. Okay, right there is the mean. Okay, I've gotten a lot better at drawing straight lines. I think I did a pretty good job on that last one. So that's the mean right in the center. Now, if you look at the location of the curve here, Does this look more like a U or more like an upside down U? If you had to give it one shape or the other, which would it be, a U or an upside down U?
Upside down.
It's certainly an upside down U here, correct? That's not really up for debate. And if you go on the far right or the far left, if you had to give it one or the other, would you call it a U or an upside down U? Is this more like a U or like an upside down U?
The U.
It's more like a U, right? I mean, it's not a perfect U, of course, but if you had to give it one versus the other, this would be more like a U, correct? So where on the graph does the graph change from being a upside down U shape to being a right side up U shape, approximately at least? If you had to give that a location, where would you say, oh, right there is where it changes? So I'm going to move along the curve, and I want you to stop me when you feel that I'm roughly in the right location for changing from a U to an upside down.
Right there.
About here, give or take.
Yeah.
And corresponding on the other side about here. This distance from the mean to that location, that distance is the standard deviation. Okay, so what we have is a way of determining the standard deviation from the graph. Okay, we kind of get we can eyeball it. Might not be 100% perfect because the exact spot is hard to do graphically, but somewhere in that location. Does that make sense so far? Any questions on that so far?
Nope.
Okay, now, if I were to go to those locations, and I'm going to make straight lines again because I'm getting really good at making straight lines. Okay, so if I go to those locations and I ask you how much of the data falls, but that was horrible. If I say how much of the data falls between those two lines in this region, oh man, I suck at this. One more time. How much of the data falls between those two spots? What percent of the data falls between one deviation on the left and one deviation on the right? Would you say if all the data? Would you say all of the data falls between those 2 points? No. We got data on the wings too. So roughly how much falls between those two spots if you had to give it a number?
95%.
No, but thanks for playing. Seeing a 95 up here and saying, oh, that must be what it is. But no, that's not what it is.
68.
Yes, it is 68%. 68% approximately, it's not exactly, but approximately 68% falls within one standard deviation to the left and to the right of the mean. For a normal curve. It's not necessarily going to be the case for something else, but it is for a normal curve. With me so far? Now, if I were to go twice that distance, if I were to go all the way now to about here, and I were to include now this part as well as this part, so I go 2 deviations left and 2 deviations right, roughly how much falls between those locations?
95.
That's 95%. Again, approximately. And if I were to go one more, 1, 2, all the way out to here, and here, and I were to include the stuff in here and here, then what percent would it be now? At least approximately.
All of it?
Not all of it. Look at my 3 numbers.
99.7.
99.7%. Almost all of it. So look at the box. What does the box say? It says about 95% of normally distributed values are within 2 deviations of the mean. Almost all, essentially 99.7% are within 3 deviations of the mean. And what they don't say, but I gave you, is that about 68% are within 1 deviation of the mean. So let's see an example. The lengths of full-term newborn babies are normally distributed with a mean of 20.5 inches and a standard deviation of 1 inch. So that means what number is right here? What X value is at the mean?
20.5?
20.5, right? That's the mean. And if I go 1 deviation out to here, what number is that?
1 more inch than that, so 21.5.
21.5. And if I go here, what's this one going to be?
1 inch less.
Well, no, I'm still moving to the right.
Oh, I thought you were on the other side.
22.5.
22.5. And if I go 1 more, what would that be?
23.5.
23.5. Now, if I go to the other side, like a normal person would do only after finishing one side, and I get to and I get to this one right here, what would that be?
19.5.
19.5. And if I go 1 more to the left, what would that be?
18.5.
18.5. And if I go 1 more to the left, what would that be?
17.5.
17.5. So now let's answer the question. 95% of newborn lengths are between what 2 numbers?
19.5 and 21.5.
What numbers did you say?
19.5 and 21.5.
So you went 1 left and 1 right, but that's not 95%.
Oh, just kidding.
18.
Look at joke.
18.5 and 22.5.
Yes, 18.5 inches and 22.5 inches. And almost all, and the word almost, or the words almost all, essentially mean, in this course at least, 3 deviations. So almost all newborn babies are between what 2 lengths?
17.5 and 23.
17.5 and 23.5, which means if your baby is full term and is not between 17.5 and 23.5, they are quite exceptional. Exceptionally tall or exceptionally short. Okay, because almost all are within 3 standard deviations. Does that make sense? Oh, someone said something here. What do they say? Let's get rid of this. So you were answering via text and I wasn't listening. Okay. All right, sorry about that. Sorry, not sorry. Okay, so let's clear it and then let's move on to the next one. So group activity. Here again is the distribution of total SAT scores, which has a mean of 1011 and a standard deviation of 216. It says complete a simplified scale for the scores using only the mean and standard deviation. That means I don't want you to put every single number in existence. I want you to put the important numbers. The most important number, of course, is the mean. That goes right in the middle. So what number goes right in the middle here? What's that?
1011.
1011. Okay, 1011 right there, smack dab in the middle. And if I go 1 deviation to the right, approximately at least, what number is that going to be?
1227.
1227, 1 deviation right. And if I go 1 more deviation to the right, what's that going to be?
1458.
Right again?
1458.
Okay, it's still wrong, but thanks for playing.
6 plus 7 is 13. I'm doing mine. The last number is a 3.
If you try again, maybe it'll change.
The last number is a 3. Hold on. 1, 2,
So what should it be?
1443.
yeah,
1,000.
1,443.
Oh, there she goes. Yeah, she's saying, yeah, that's what it is.
I was doing it literally in my composition book.
Okay. And if we go 1 more, what do we get? Okay, good talk.
1,659.
Okay, and how about if we go the other way? What if I go one deviation down?
795.
Who used a calculator there? 795. And if I go one more,
579.
579. And if I go one more,
363.
ooh, look at you jumping ahead.
Sorry,
We're
Solar.
so excited of that.
No, thank you.
Okay, so this is a scale for the scores. Now, if I asked you what percent score between 795 and 1227, at least approximately, what would your answer be? What percent score between these two numbers?
68.
68%. And if I said how many score between 579 and 1443?
95.
95. And how many score between 363 and 1659?
Then 99.7.
99.7%, almost all. Of course, we all know that SAT scores end at 1600, or at least they did in my day. Then they changed, and I think they changed back, so they're kind of all over the place. I think so, right? You had they had like an essay, and then they got rid of it or something like that. I don't know.
I
Whatever.
think they're still 1,600, but yes, with essays.
Yeah, so that's why this is approximately normal, because normal in theory goes on forever in both directions. And of course, here, SAT scores do not go on forever in both directions. In fact, I don't think you can get less than a 400 or higher than a 1600. So again, it's only an approximation. Okay. So let's see what comes next. Oh, I already answered that. Okay, so both these next questions we already answered. 95% are between whatever those two numbers were, and almost all are between whatever those two numbers were. We just did those questions. So let's combine this together with something that we've done before. Example. A total SAT score of say 1230 can be meaningless to students, so a measure of position such as a percentile is reported. You guys remember what a percentile was? It was part of the last quiz. What's a percentile? When you give a percentile, what are you giving? What are you saying?
You're saying that all the values are below or at that percent. Was it that?
It was not, but thanks for trying. Try again tomorrow. Someone want to tell me what a percentile is? If I say like you scored in the 84th percentile, what does that mean?
You scored
That means that
as good as or better than 84% of the people.
You scored better than 84% of the people, which means if I go back to
I thought it's the opposite.
no, if you're in the 84th percentile, you are better than 84%.
Professor?
Yes.
Oh, yes.
Doesn't that mean 84% of people or 83% of people are below you?
Hey, can't get anything by you. That's right. So where exactly on this display, approximately at least, would a score be if you scored in the 84th percentile? Would it be somewhere on the left, left, middle, moderate right, or far right? If you scored in the 84th percentile?
Moderate, right?
Yeah, it would be somewhere like over here somewhere, right? Because we want 84% to be to the left of it. Now, of course, that's not really exact. So let's see if we can make it exact. Let's see if we can figure out exactly where the 84th percentile is, knowing your score, the mean, and the standard deviation. And the answer is you can. So it says here, interpret the meaning of the 84th percentile. Doesn't mean, for example, that the student got 84% of the questions correct. Not even close, right? It's all about how you did relative to anyone else. Okay. So what is the percentile for a score of 1011? That's an easy one. What's the percentile for a score of 1011?
50%.
50th percentile, not 50th%, 50th percentile. Okay, you were right smack dab in the middle, right? If you're right smack dab in the middle, that means 50 people did worse, 50% did better, correct? That's the 50th percentile. Is it possible that a score of 1,000 falls at the 20th percentile?
No,
No.
Why not?
because then it wouldn't be a bell-shaped curve.
No, that doesn't answer it. I mean, here you have 1011, right?
Too far to
Does
the
it get
left.
close to
It's
the
way
median?
too far to the left because remember, one deviation to the left was what number again?
795.
795, right? Now, let's do a little thinking. If I go one deviation right and one deviation left, what percent fall in that area?
55.
That's 68%, right? That's the number I gave you, right? One deviation left, one deviation right, 68%, correct?
Yes.
That leaves how much for each of these little wing areas? If 68% in the middle, how much would be here in the right wing?
32.
Hold on. It has to add to 100%.
16.
Half of 32.
Half of 32, right? If 68% is in the middle, 32% is left. Half of that is how much?
16%.
16%. You agree with that?
Yeah.
Which means a 795 would be what percentile?
What was the question?
68.
No. Think. Don't just look at numbers on the page and say, "Oh, it must be that." Think. Think about what the definition is. If I score 795,
84% is that whole topic.
sorry.
I'm thinking to myself.
Oh, okay, I did that once. So 795. When I ask you what percentile it is, I'm saying you scored better than what percent of people?
16.
16.
16. This is a 16th percentile. Because you scored better than 16% of people, approximately at least. So the question on the page was, is it possible that 1000 is the 20th percentile?
No.
Well, 1000 is just to the left of 1011, correct? That's 1000, correct, right?
Yeah.
Does it seem that we're going to jump from the 16th percentile here to the 50th percentile here and have this be the 20th percentile?
No.
That doesn't seem very likely at all, right? Mathematically, the 20th percentile should be a lot closer to this side, correct? Maybe 805, 810, 815, I don't know, somewhere around there, correct?
Yeah.
So we can just tell just by looking at a few numbers that it does not really make a lot of sense. But the goal still is, can we determine the exact percentile that a score falls in? Okay, and the answer is yes. Okay, and that's what we're going to do today. Okay, so just you should know when tests are normally distributed or anything is normally distributed, there's two types of measures of position that are often used: z-scores and t-scores, and we're going to use both. Okay, in our work, we're going to use both z-scores and t-scores.
Okay.
And I promise I'm going to show you how. Questions so far? Any questions so far, or it's good so far?
Good.
Good, okay. So let's go to the next slide, which is a slide on z-scores. A z-score is the number of standard deviations a score falls from the mean. Okay, what that means is if your z-score is 1, then you fell precisely 1 standard deviation above the mean. And if your z-score is -1, you scored 1 standard deviation below the mean. So in this example here, what score would correspond to a z-score of 1?
115.
115. What z-score would correspond to a standard deviation of 2?
130.
130. How about -1?
85.
85. How about 0?
100.
100, because you're actually at the mean. How about 70?
-2.
-2, and so on. Does that make sense? So all these, so the idea of a z-score is how many standard deviations you fall from the mean. Now the question is, if I don't have a graph, is there a way that I can compute that? And the answer is yes. We have a formula for it. The formula for a z-score, you take your data, whatever your data point is, and the last example was like, what, 1,000, right? You take your data, you subtract the mean, and you divide by the standard deviation. So let's do an example from the situation that we just did, which was a mean of, was it 1,011? Right, we had a situation where the mean was 1,011 and the standard deviation was what? 216 would it be?
Yeah.
Wait, someone asked a question. She goes, what would the z-score be for 110? The answer is 2/3. Right? If you're at 210, you are 2/3 of a deviation above the mean, correct? Because each deviation is 15. So if you're at 110, then you are 2/3 above. Will you agree? Okay. So what will be the z-score for 1,500? What will be the z-score for 1,500?
You would do 1,500 minus 1,011 divided
Yes.
by 216.
Excellent. You take your data point, which is 1,500. You subtract the mean, which is 1,011. And then you divide by the standard deviation, which is 216. And when I do that, where did my calculator go?
I got 2.26388.
Okay, so we'll say approximately 2.63.
2.263. So yeah.
Oh, sorry, 2.263. Correct? Did I hear that right? 2.263. Okay, we'll say 2.26. So what does that tell us? Where do I fall if my z-score is 2.26?
Like a little over 2 standard deviations from the mean.
Excellent. I mean, it's more exactly, it's about 2.25.
2.25.
Right?
Mm-hmm.
What if my z-score is 940? What would I do?
Minus 1,011 divided by 216.
You have to subtract 940 and 11 or 10,000.
Exactly. So you take 940 and you subtract 1,011.
Wait, Professor.
Yeah.
For the 1,500,
Yeah.
would we say like 2.25? Would we say like it's above 130?
Well, I mean, you want to be as exact as possible. I would say it's a little more than 2.25.
So
Okay.
should we use the fractions? I mean, like the decimals or the fraction?
In this case, you want to use decimals.
Okay. What about on a test?
Yeah, same thing on a test.
Okay, decimals. Okay.
Yeah. I mean, I really don't care one way or the other, to be honest. It doesn't make a difference to me, but I personally use decimals. So what do you get? Negative 0.3287, which tells me what? Where does
It's below the mean.
it's below the mean, but how far below the
You're
mean?
not exactly one deviation below the mean, but you're just like, I don't know if you're a little bit.
A little bit over a third.
A little bit over a third.
Yeah, there we go. Better.
Wonderful. A little bit over a third. Excellent. Okay. Okay. So now using z-scores to make comparisons. Okay. Using z-scores to make comparisons. So Kim is 5 feet, 2.5 inches tall. And Kanye is 5 foot 8 inches tall. I don't know where these names came from. These are pretty weird names, and I'm not sure what those pictures got to do with anything, but whatever. Now, men in general are 70 inches tall on average, and women with a deviation of 3 inches, and women in general are 65 inches tall with a deviation of 2.6 inches. So, which one of those two, if either, is unusually short? Okay, so what we need to do is we need to compute their z-scores and see if either one of them is under 2 deviations below the mean. If someone is under 2 deviations above the mean, below the mean or above the mean, we call it unusual. Unusual means outside of 2 deviations. Almost all is 3 deviations, but unusual is 2 deviations. So let's compute their z-scores. Let's do, who should we do first? Kanye or Kim?
Oh, let's do Kim.
Okay, Kim first. What is Kim's height in inches?
62.5 inches.
62.5. And we subtract the mean of women, which is how much?
65.
Which is 65. And then we divide by the standard deviation for women, which is how much?
2.6.
Which is 2.6. And what do we get? Let's do the math.
Negative 0.011.
Hold on. Divided by 2.6. Negative, what was it? I'm sorry again?
0.011.
Negative 0.011. So would Kim be unusually short?
No.
No, in fact, she's actually right about average, right? She's right in the middle for the most part, right? I mean, her z-score is so close to 0,
Mhm.
it's essentially 0. So let's now do Kanye. Okay.
I hope he wins for
I got a
president.
different answer for.
I got a different answer too.
I
For
got
the
negative
one?
0.961.
Yeah, that's
Exactly. Yeah, I got negative 0.961 as well.
Uh-oh.
What? Where?
That's what I got too.
Well, I'm just trusting you. You guys leave me wrong.
Terrible.
It's your problem. So
Terrible.
You've been pranked.
what is negative what?
Been punked. Sorry.
0.961.
Okay, 0.961. Well, that changes things a little bit in terms of how average she is, but it does not change the fact that she is not unusually short. Agreed?
Right.
Okay. Now, what is Kanye's z-score? Well, what is Kanye's data point?
68 inches.
68 inches. Does it say that? 5'8", yeah, 68 inches. Okay. And what is Kanye's, or men in general, what is their mean?
70.
70.
70. And what is the deviation for men?
3.0.
3. So we get negative 0.67 approximately. So we see that neither of them is unusually short. Would you agree with that?
Mm-hmm.
Okay, next question. Who is taller compared to others of their gender?
Kim, right?
So Kim has a lower z-score, right? So Kim is further to the left from the middle than Kanye is, right?
Wait a second.
Do I have to?
Yeah. Okay.
Right? So Kim is 1 deviation down approximately, whereas Kanye is 2/3 of a deviation down, right? So Kanye is taller in regards to other men than Kim is in regards to women. Does that make sense?
Yeah.
Everyone make sense? Questions on it? Seems clear.
Can you clarify that one more time?
So Kim's z-score is about -1, a little less than -1, right? So that means that Kim is 1 deviation below the average for women.
Okay.
Kanye's z-score is -0.7 approximately, which means he is only about 2/3 of a deviation below average for men. Which means,
so whatever is closest to the mean would be the one that has.
well, whichever one's to the right is the one that's higher in relation to their demographic.
Okay.
In this case, it's heights, with gender, but other problems can be completely different. But the best way of comparing 2 different demographics, because you can't compare men and women, we're physiologically have different heights, but you can still look at their z-scores to compare them within their own gender to determine which one is more unusual. In this case, they're both pretty unusual. Not because of their heights, just because they're very weird people. Okay, so let's move on. Huh? What was that? Sorry, tell me what? Okay.
I had a question on the z-scores.
Yeah, go ahead.
What would make it an unusual answer?
An unusual answer is one that is beyond 2 deviations above or below. So if you're 2 point, 3 point, 4 point, if you're past 2 deviations, we call it unusual, whether it's below or above. So in this case, neither of them were beyond 2. One was -1, one was -2/3.
Okay.
Agreed?
Okay, so 2 deviations, basically.
2 deviations is considered unusual. If you're beyond 2, you're considered unusual. The middle 95%. Now just be aware, 95% is 19 out of 20. So they're basically claiming by that standard that 1 in 20 is considered unusual. And that's just the way it goes. That's what we say. 1 in 20 is unusual. Okay? So now what we have in front of us is a z-table. A z-table, notice first of all, we have a bell curve. Okay, you don't have a z-table without a bell curve, otherwise it's not a z-table. And what it does is if you give me a z-score, the table tells you the percent below that z-score. So for example, if z is 0, if I'm here right in the center, then what is the percent below that z-score if z is 0? Don't look at the table, you can do this in your head. What percent is below 0? 0 deviations, right in the middle, what percent is below it?
50%?
50%, which is why if my z-score is 0, I have a proportion below it exactly equal to 50%. Do you see that? Or do you not?
Why is that the case if the line is not like directly in the middle?
Well, no, the lines, which line are you talking about?
Like, you know where it says Z and the line, it doesn't matter that it's not directly in the middle to be 50%.
No, this is a generic Z. I asked you what would happen if Z was 0.
Oh, okay.
These are all different possibilities for Z. And each one of them gives a different percentage or proportion below. If Z is 0, if it was in the middle, it will be exactly 50% below.
Okay.
What if Z was 1? What percent would be below 1?
84.
About 84%. Does that jive with my 68, 95, 99.7 rule?
No.
Then why would I have it be a rule if it doesn't jive? Right? These
Are we
rules,
looking for our 68 and our 95th and our 99.7?
no, I just said, does having a value of 0.84 with a z-score of 1 jive with the rule that I gave you of 68, 95, and 99.7? Now, don't just answer one yes because you think I'm looking for it, but think about it. Does it jive that a z-score of 1 should have a proportion below equal to about 84%? Well, let's, z-score of 1 is about right here. Jive means does it work with it? Do they work together?
I think it does, because if we look at the table, it's more towards like the 84%. Like it makes sense from what you said.
Well, forget about, I mean, yes, but let's not even talk about what I said. Let's talk about something a little bit beyond that, which is the 68, 95, 99.7 rule says that if you go 1 deviation in either direction, what percent is going to fall in that region? If you go 1 deviation in either direction. 1 deviation left, 1 deviation right, what percent?
That's 68% of the data.
68%, which means how much is outside of that 68% of the data?
32%.
And how much is on the right side or the left side?
16.
16. So if I have 16 here, how much is to the left of that point?
16?
No.
The left of what point?
Of this guy
Eight.
right there.
68.
Huh?
Oh, left.
Left.
68.
No. The
84%.
84. There's 16% to the right. So there's 84% to the left. It's got to add to 100%. Right? All of this area here to the left of this point. If there's 16% to the right, there's got to be 84% to the left.
Yes.
Well, that means that it's in the 84th percentile.
Oh my gosh. I was looking at the -1.
Well, that's an issue.
Yeah, it jives.
It jives. Float your boat. Does it sound race? Does it sound? Yeah, if things jive, they go together. In other words, if I say, something like, all men are under 3 feet, but I'm 9 feet. Oh, that doesn't make any sense. But I'm 5'8", 5'9", whatever. That doesn't jive. Those two things don't go together.
Sorry, I've never heard that term like that.
Never heard jive?
Yeah, but jive is also like bullshit. So, like when you're driving somebody.
What?
So, yes.
Does that jive? Jive means to be in accord, to agree. But to confuse matters, jive also means to shift your sail from one side to the other. That doesn't mean anything. Does that jive? Jive is okay.
Look in the Urban Dictionary.
Like the hand jive, like they do like in Greece.
Yes.
Hey, watch your language there, buddy. So does
Right.
it jive? Right? I don't know. Whatever.
He's jiving you, see?
Jiving you.
Interesting.
So I was the only one confused, right? Or was
Fair
I?
enough.
You're
Okay.
good, Tomas.
Okay. So anyways, so the way we do z-scores, if you're ever wondering what percent is to the left of a certain value, you compute the z-score and then you go to the table. Like, for example, the ones we did a few minutes ago. What do we get for 1500 on the SAT? What was our z-score for 1500?
2.26.
2.26. So I go to my z table, and let's say I go to 2.3, let's say, which is the closest value. That tells me that 0.9893, that about 99% of my data points are going to be beneath it. Where is 1500 on my SAT thing in the very beginning?
The far right.
The very far right. Does it make sense that 99% are beneath it?
It jives.
It jives. That's right. She's got it. It jives. That's right. So we're going to do some examples of this. Let me erase this and let's do some examples. Okay. So what is the percentile for height for Kim? So what was Kim's z-score?
-0.962.
Negative 0.962. That was her z-score. So what we're going to do is go back to my table and look for a z-score of negative 0.962. That's between these two numbers here, right? Negative 0.9 is this, negative 1 is this. It seems to be about halfway in between. So I might take about halfway in between these numbers, like what, 1.72 or something like that? 0.172, give or take.
Professor, if we were to just round up to -1.
Well, we're only approximating anyway, so I really wouldn't worry about it. That's first of all. Okay, we're only approximating. Second, better tables round to 2 decimals, not 1, which is already a huge advantage. And third, calculators or online calculators will round to like 10 decimal places. So they'll give you like really, really much more precise answers. Let me show you just, by the way, an online calculator, just so you see what I'm talking about. So I'm going to do a z-score calculator. What was Kim's Z-score again?
Negative point
Oh,
nine.
actually, even better. What was her actual value?
0.962.
No, not her Z-score. Her actual height. What was her raw score?
Oh,
62.5.
60 points.
Oh, no.
Oh,
5.
62.5.
62.5.
She's
And
five.
what was her mean? What was the mean for women?
265.
65.
5.
Sorry.
65. And what was the deviation for women?
2.6.
2.6.
2.6. So let's calculate her Z-score. Her Z-score is negative 0.96154. Negative 0.96154.
That's what we calculated in B.
Yeah, we already got that.
You're right. That was stupid of me. So let's go one step further. And let's do note. If you already know the value of Z and want to calculate P, this calculator will do the job. Okay. So what was the negative 0.96 what?
2.
962 exactly?
Well, 961 something, but 962.
Well, let's get the exact value. That was negative 0.96154. Okay, and actually, I don't think that's what I want. I don't want the p-value. Okay, let's do negative 0.96154. Hold on, let's get another calculator. Let's do this one. Here we go. Negative 0.96154. And we want the probability of being less than that number. And here we go. That's the answer. The probability of being less than negative 0.96154 is 0.16814. 16.814%. Does that jive? Huh?
You wouldn't just take the two values, add them up, and divide by 2?
That's an approximation, but because it's a curve that does this, it's not exactly the average. But what you can see here, 0.16814, and we got between those two numbers, we see it's not half bad as an approximation, right?
How would we compute that though?
How do we what the computer did?
Yeah.
You don't. You put it into a calculator, do it for you.
Okay.
We do not do that by hand. Okay, we can't do that by hand. If you actually would study the more advanced math of behind this, you would learn that you cannot do it by hand, and only a calculator or a computer.
How would you put that into the calculator?
Oh, what kind of calculator do you have?
The T181. What?
This TI?
Yeah.
I'll show you exactly. Even if you don't have one, you can follow along. So, just to show you, for those who have the TI-84, I'll tell you how to get to where I'm going to go. You hit second, the blue second, and if you don't have it, don't worry, second. And then you hit VARS, V-A-R-S, right here. And it goes to this page. Okay, and you are going to go down to normal CDF. The second one on the list is normal CDF. And that gives you something that looks like this. Okay, you with me so far?
Mm-hmm.
Okay. Now, the lower is going to be negative infinity because we want to go all the way from negative infinity up until Kim's height. What was Kim's height again?
62.5 inches.
62.5. So for Kim's height, for my upper, I put in 62.5. What's the mean?
65.
65. So I put in the mean of 65. What's my deviation?
2.6.
So I put in 2.6. And then I hit enter. And it gives me that value. 0.168140738.6. So does that make sense?
Yes. Now, next question: would we be able to just add them and divide by 2?
No,
Okay.
you can't just add them and divide by 2 because adding them and divide by 2, well, I guess,
It gets you like 0.171.
okay, it's going to be close. but depending on the kind of precision that you're after, it might not be close enough.
Okay.
Or it might be close enough. It's hard to say without
Right.
knowing the precision that you're after. Okay, fair enough? Okay,
Follow-up question.
yeah, go ahead.
On a test, would you want us to be exact as possible?
Always, within reason.
Okay.
Yeah, I mean, if being exact as possible requires you to do, you know, a 10-page long division, you know, mathematical calculation, which is theoretically possible, obviously I wouldn't expect that.
So you'd encourage us to use the calculator, either the graphing calculator or online.
Yes, I 100% would, because
Okay.
that's what I would do.
Professor, can you put the link for the website you were on in the chat?
Oh, I just did a Google search. I did Z-score calculator.
Oh, okay.
And it was I think it was that one. You know, again, there's no one that's better than all others. So I just picked one at random. No, the first one that I picked didn't work, so I had to pick a second one. Right? But this one, Z-score calculator, calculator.net, that seems to be the one that worked. Okay. Whoops, wrong button. Okay. Oh, I didn't mean to do that. Sorry. Okay, I meant to hit. Okay, so moving on. Okay, so we don't have to do Kanye. Okay, let's do this one. To identify students of high achievement ability, the LAUSD tests all second grade students using the Otis Lennon School Ability Test, the OLSAT 8. The first 7 weren't good enough, but the 8th one seems to do the trick. This, nobody laughed, but I thought it was funny. Anyways, this test has a mean of 100 and a standard deviation of 16. To qualify, the student must have an age. Oh, someone texted, said, I laughed. You just didn't see me. Or something. Ha 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 ha. No, that doesn't work. That's so pedantic. Okay, so anyways, to qualify, the student must have an age percentile rank of 95 or above. If the student is of low socioeconomic status, an APR of 90 is sufficient. So what Z-score does a non-low SES student need on this test to qualify as high achievement ability? What score must be necessary for a normal, I don't want to say normal, but not someone of low socioeconomic status to qualify for high achievement ability? How would I calculate that?
You have to find what the 90th percentile was.
Is it the 90th that we're after?
The 95th.
So 95th, right?
Yeah, 90.
Now, if I go above 95th percentile corresponds to a score between 1.6 and 1.7. Right? As you can see here, 1.6 is the 94.5 percentile, and 1.7 is a 95 and 5/4 percentile. So I can tell you just from experience, the 95th percentile happens to be at 1.645. So we want to get a score that corresponds to a value of 1.645. The question is, what score with a mean of 100 and a deviation of 16 corresponds to a Z-score of 1.645? How would I go ahead and do that?
You could graph 2 standard deviations out and see that 132 is at the 95th.
So the problem with graphing is it's not very exact.
Aw.
We want a more mathematically precise answer for 1.645 as my Z-score. And the answer is just use the formula for Z-score. But now we know Z, and what we don't know is the raw score.
How would you do it?
Could you just do kind of like regular algebra? So I got what, n or whatever, n minus 100 over 16 equals 1.64.
Yeah, 1.645 more specifically, yes.
And then you just multiply by 16 to cancel that out. And that got me 26.32 on that side.
And then you add 100.
And that gives you 126.32 for n.
And there's your answer. Does
All
that make
right, Tomas.
Sorry, what was that? Oh yeah, come on, guys. Come on, guys, give the guy props.
Woohoo!
Everyone's wow. That's one person prop. That's kind of weak.
Hey, you write it though, because he went super fast.
So you multiply 1.645 times 16. We got 1.645 times 16 equals x minus 10. Sorry, not a 10, 100 I meant, I'm sorry. And then add 100 to both sides. So we get 1.645 times 16 plus 100, and we get 126.32.
Professor, where'd you get the 1.645?
I gave you that. That is the number for a z-score of 0.95, sorry, 95th percentile corresponds to 1.645. Fact, memorize or write it down. Okay, a z-score of 0.95 corresponds to 1.645. Yes, Tolaire?
So what if you didn't have that z-score table? How would you be
You
able
wouldn't.
to
Use a calculator.
Oh, okay.
Use a calculator. You don't do it by hand. Okay, now, what score on the LSAT 8 does a non-low SES student need to, didn't we just do that one, non-low?
That's probably a typo. They probably mean.
Oh, no. First they asked what z-score. That was my bad. First they asked what z-score, and the answer is 1.645. And then they asked what actual score, and the answer is 126.32. I combined them together into one problem. The z-score is 1.645, and the actual score is 126.32. Okay, let's do another one. Who's that? That is Taylor Swift. Taylor Swift is at the 97th percentile in height for young women. She is tall. The mean is 65 inches. The standard deviation is 2.6 inches. The question is, how tall is she? How tall is Taylor Swift? So how do I do that? How tall is Taylor Swift? Well, we have her percentile. Her percentile, how tall, Paul? We have her percentile is 97th percentile, correct? So let's go up and let's figure out what z-score corresponds to the 97th percentile. Find for me in this table the 97th percentile, at least approximately.
1.9.
So the 97th percentile is about 1.9. Do we agree? This is a lot closer to 97% than this one is. So I would say a little under 1.9, but we'll just pretend it's 1.9. So her z-score is 1.9. Okay, so where does 1.9 fall on the charts? Where is 1.9 on the chart, huh?
About 2 deviations, standard deviations away.
Yeah, about right there, right? About one, a little bit less than 2 deviations, correct? Because it's not 2, it's 1.9, but it's fairly close, right? Okay. Now, find her height. How tall is she? Well, we have the z-score, which we just calculated is 1.97 or 1.9. What do we get? 1.9 equals her currently unknown height minus the mean for women, which is how much?
65.
65 divided by the standard deviation for women, which is how much?
2.6.
2.6. So let's see how tall she is. So what do we get?
114.4.
That doesn't make sense. Try again.
What am I doing?
Something wrong.
9.94.
How much? Yeah, 69.94. Now, 12, 24, 36, 48, 60. She's about 5'10". So she's taller than me. So she's tall. I didn't know that about her. And now that I do, my life is complete. I will go on to live a life of religious fulfillment. Okay, next example.
Wait, Professor, I'm sorry. How did
Yes.
you get that?
How did I get what?
Her height. I'm lost.
Can I undo it? You cross multiply. This is exactly the same math as the previous one. You cross multiply and then you add. Right? You multiply both sides by 2.6 and then you add 65.
Oh, okay, got it. Thank
Okay. So the CDC says that a definite case of Zika-related congenital microcephaly. Thank you. Microcephaly occurs when a head circumference at birth is less than the 3rd percentile for gestational age and sex. Don't understand a word I just said, but for a full-term girl, this would be a HC less than 31.7. The mean's about 33.8 with a standard deviation of 1.12. Assuming the distribution is normal, check the computation that an HC of 31.7 falls to the 3rd percentile. So let's compute the z-score. What is a z-score for 31.7? What's the z-score? Huh?
Oh, that's that's 0.
Data point minus mean over sigma, over the deviation. That's the formula for the z-score. Data point minus the mean divided by the standard deviation. So what do we get when we plug into the calculator?
I don't know if I'm right. I got negative 1.875.
Well, so Larry, you are never wrong.
I've been wrong all day.
I know, I was just being facetious. Okay, so negative 1.875. I was trying to be nice in a sarcastic way that would really indicate that I wasn't. Hoping you wouldn't catch it, but you did. That's okay. So negative 1.875. The question now becomes, what's the percentile for negative 1.875? Well, let's go all the way back to our table. A z-score of negative 1.875 falls where?
Closer to negative 1.9.
Close to negative 1.9, but in between negative 1.9 and negative 1.8. And according to this, what is the percentile for that z-score? Does it jive?
No.
Yes, it does.
Oh, it does. Sorry.
The percentile is right around 3%.
Yeah. There we go.
So it jives. Megan, it jives.
It drives. Yes.
It jives. Okay. Wow, I can be annoying at times.
Wait,
Okay.
why does it jive again?
Why does it jive? Megan, tell him, why does it jive?
Because wasn't it around the score that was given to? Like, you have to go down. I don't remember what the score was given.
Because it said
31.7.
Yeah.
It said that
So if that score was 31.7%, right? I'm going in that right direction. It's driving. So negative 1.8 over here. I'm clicking like I can show him. Negative 1.8 has the 35-ish percent. So it's not like far
Not
off.
35-ish, 3.5-ish.
3.5-ish, sorry.
Okay, 3.6% of negative 1.8, 2.9% of negative 1.9. We're closer to negative 1.9, so it looks like we're about 3%.
Wait.
What does the 3% have to do with anything?
Well, the question said,
we're double checking it.
we're double checking. The question says the CDC says that if you're less than the 3rd percentile, then you have this condition. And then they said, that's a 31.7. And we're like, is it? Let's check. So we found the percentile for 31.7. And sure enough, it's 3%. So we were just checking the CDC because, you know, you never want to take for granted anything that the CDC says because they are liars.
So percentile is percentage? I thought it wasn't.
Percentile gives you, when I say the percentile, like the 10th percentile, that means 10% of my data is beneath that point. So percentile and percent are connected in that regard. The percentile is the score. The percent is what's beneath that score.
Okay.
10th percentile has 10% beneath it. Verdad?
Yes.
Okay.
So professor, if it would have said the first percentile, then no jiving, right?
Then no jiving. Those are lying sons of bitches. That's all I can say. Those CDCs, don't trust a word they say. Okay. So the T-score, by the way, I was just kidding about that. CDC, very reputable. They're a great organization. Just if they say something like is bad for you, just don't do it. Okay. So T-score. Students and parents find a Z-score such as -0.5 difficult to understand. How can my child get a negative score on a test, they say? Thus, T-scores frequently are used instead. To compute a T-score, first compute the Z-score. So you got to do that anyways. Then multiply the Z-score by 10 and add 50. So if I got a Z-score of 0, for example, then what would that T-score be that corresponds to a Z-score of 0?
50.
It will be a 50. Okay. So basically, if 0 is right in the middle, then a T-score of 50 corresponds to being right in the middle. Make sense?
Which makes that the mean?
Which makes it the mean for the T-scores. Yes, exactly. Okay. And in fact, that's what they're asking here, right? What is the mean and deviation for T-scores? Oh, almost done. Oh, we're running out of time. Oh, we're so close to finishing. We're so lucky, guys. Oh no, we'll have to hold off on this and finish it very quickly next time because we're out of time and I don't want to spend any more time than I have to here because I want to go to sleep. So we will finish this next time. And we'll probably have a quiz soon as well. We should maybe have a second test soon, no? I think it's coming time for a test. What do you guys think?
I think we can do a midterm and then a final. So we technically did a midterm already.
Oh, really, Soler? Thank you so much for that offer. Wow, that's so generous of you. Oh, well, there would be less grading for me, which is never a bad thing. But
yeah, I agree with Soler. Let's go for her plan.
you like her? You like Soler's idea? What if you do bad on the final and you don't have enough tests to kind of balance that?
Then there's a retake.
I don't think there's a retake for the final.
Or
the word final literally means final. It's like the end. You can't just like say, well, after the final, let's do something.
You can give us a quiz and call it a test.
Oh,
that's a good idea.
No, do that. Do that.
Test.
That definitely jives.
That jives.
That jives.
That jives with what? You can't just say it jives. You get two things jive, not one thing.
With all of us not having a panic attack, please.
I see. Come on, this class has been great. What are you talking about? You guys are loving it. This class is awesome. Admit it. Best,
it's been fun,
best college class you've ever had in your entire life.
I'll admit it's the best math class I've ever had, but combined with all my other classes, I think I need a mental break.
Yeah, me too, sister. All right. Anyways, we'll talk about it next time. But I'm going to stop sharing right now, and I'm going to stop recording right now.